Welcome friends once again to the NPTEL MOOC module on exploring health data. We are on the verge of completing the 5th week. Here we are picking off one of the very pertinent topic which is mostly discussed in research or is required for writing research papers. This is one kind of post estimation check. We have kept the title of this particular lecture is on measures of variation, may be explained by small r square, capital R square, adjusted R square or pseudo R square. There are many doubts with researchers, and they usually cut off with this confusion how to deal with each of these issues, which is very essential while writing papers. Reviewers will check some of these indicators very seriously to understand whether your models are perfectly all right or not. In this regard, we will clarify further details through our lecture. So, this is measures of variation is also called goodness of fit. So, goodness of fit is not only important in ordinary or linear regression analysis, but also in logistic regression analysis as well. In the linear regression, that is OLS, the coefficient of determination is basically called small r square, capital R square and adjusted R square, and is the universally acknowledged measures to quantify the quality of a regression models and its fit. Pseudo R square has been proposed for use in the limited dependent variable models, especially logit. So, what do you mean by goodness of fit? This is basically how your model is perfectly fit as per the variables, and what is this average trend line. Okay. This explains the agreement between observed data and the data generated by a model. So, the observed data and the data generated by the model, any difference between these is actually explained with the help of goodness of fit. Goodness of fit tests are statistical tests to determine whether a set of actual observed values match the predicted values of the model. So, the model which predicted is actually matching with the actual observed data or not. If it is not matching, then there is certain problem with the goodness of fit. So, a model may be incorrect. So, like goodness of fit, as we already said, we need to understand when and why does goodness of fit apply. Okay. Goodness of fit is important when the model is focused or or oriented, but less important when we focus on single effects, that is factor orientation. Okay. There are two understanding, two way by which we should understand the orientation. One is called the entire model orientation, another is called single effect orientation. In case of single, it is not that important, but in case of the entire model on a whole, goodness of fit is mostly discussed and has to be understood correctly. A model oriented or approach requires the inclusion of all systematic sources of variation on the outcome. Model oriented approaches try to answer questions like what explains the outcome. Okay. Now, from this chart, from this diagram, you can easily understand how our model is actually perfectly fitting to the trend line. So, trend line equation you can simply get it in Excel as well as in all the packages. Now, it seems there exists a strong correlation between these two variables. So, if you have different control variables, we wanted to map with its explained variable. We can see that it follows a perfect trend line. So, this gives rough idea about goodness of fit as well, but not exactly goodness of fit. We are now clarifying how we can able to measure those variation. If the variation is very huge, that means it is not perfectly fit. When it is near about the trend line, that means the variation is less. We need to understand its statistical significance of those variation and accordingly clarify whether your model is going to be fit or not. Now, first concept in this case is called observed y. then then some extend to explain portion of the individual data of that is y, then unexplained portion of yi. So, these three concepts mathematically should have been clarified. So, so yi which we have mentioned as observed, that is based on the estimated beta values, okay, of x and the control variables, and it is for the model we have mentioned here. Okay. Then explained proportion of yi is finally based on the estimated value of the yi hat, that is basically considered with yi hat. Okay. And unexplained is basically the error, the estimated error. The estimated error explains the unexplained portion of yi that is not explained through the model. Okay. If that gap is going to be higher, then actually there are certain problems in the model. Okay. So, that is basically the difference between observed yi minus the explained portion of yi or estimated value of yi. So, this is basically the epsilon, and this is what we are going to estimate in short. Then what is this variation in total? How we can clarify the variation? Variation is through three important concepts. One is called sum total of squares or total sum of squares, TSS, okay, or SST as well, sum of square total. This measures the variation of yi values around their total mean, okay, that is y bar. Y bar you have to clarify these things, y bar and then y hat. Okay. So, this is basically each individual observed values minus the population average or the total average is basically capturing the difference. This difference is called total sum of squares. Then second one is called regression sum of square. It is basically from the mean values for sure, but the estimated yi, not the individual yi. Estimated yi hat and its sum of squares. Okay. So, minus y bar if we take its square values. Okay. The difference between these two is basically called regression sum of square. Then that is basically called explained variation attributable to the linear relationship between x and y. Due to the linear relationship between x and y, which we derive through the regression analysis, if there are any variation, that is basically captured through the SSR or regression sum of square. Then SSE, error sum of square. Now, each explained variation, that is yi hat, okay, and through the individual observed values, estimated values and observed values, if there are certain differences, that is basically called error sum of square, which we have just explained couple of minutes back. Okay. So, now it's the square has to be every time we take the attempt to minimize the square in linear regression model, but here we are saying that if the square is since we are taking in positive values, by taking a square, those squares can be now comparable. So, variation attributable to factors other than the linear relationship between x and y is basically called these differences. So, what is this SST, SSE and SSR? Now, you can just see this is called total sum of square. What is this total sum of square? It is basically each values, each yi values minus the y bar, okay, minus y bar. Y bar we have mapped it here. So, y bar each value, that is from the point here till the y bar point, the difference between these two and its square is equal sum of squares total. Okay. And that is called total sum of square in any model. Now, sum of square due to regression is given here yi hat minus y bar. So, y bar we have already explained as this. So, due to the regression trend line, trend line and its different, whether the trend line is in fact fitting to the average trend line of the total observed values. Okay. The trend line values or the estimated values is explained through this, okay, that this is basically called y hat, okay, and the total mean of the average value, this is basically mean of your regression line or mean of your or estimated value through the regression, okay. Minus the total mean, which is basically constant, since we are mapping it is here as y bar. So, each difference value of y hat, every time the difference is, this difference is basically called regression sum of square. Now comes your error sum of square, which we have just mentioned. It is basically it is the error. Error means what? Each values that is provided minus the value on the average trend line or the estimated value we have derived. How each value is different than that of the estimated value. If that difference is if we can plot it, basically called sum of square errors. All right. Now, how we are going to define the measures of variation? We are going to take certain ratios. So, those ratios will explain us about coefficient of variation. So, now let us clarify one by one, is called small r square and capital R square. Small r square is basically two variable case, it's a binary relationship, that is called two variable relationship, not multiple relationship. So, in that case two variables if you are taking, it is simply called small r square. Usually small r is taken the correlation coefficient of two variables, okay. But capital R, if you are taking, that is called multiple correlation, okay. Capital R is for multiple correlation, small r is called correlation between two variables, bivariate correlation. Similarly, its goodness of fit or its coefficient of variation in this context is written as small r square and capital R square. So, capital R square and small r square is in fact a summary measure that tells how well the simple regression lines fits the data. Small r square and capital R square measures how big proportion of the total variation in the dependent variable is explained by the independent variable. How much its variation is explained by the independent variables. Then capital R square is usually called the multiple coefficient of determination. Okay. So, next we are clarifying the differences. R square generally used in single equation model. This model explains only one independent variable. Okay. Now, here like in this example you can see some overlapping, okay, and there is x and y, there is complete differences. There are certain portion of overlapping like this. Now, R square value in case of the diagram B, then B, C, D and E, okay. So, like is within the range of 0 and 1, okay, within the range of 0 and 1. If there is no correlation at all, no explanation by the independent variable, in that case it is going to be 0. If it is 100% explained, 100% explained by the independent variable, then that is, in that case it is called 1. Okay. So, that means the variation is accordingly measured. Let us explain it further. What do you mean by coefficient of determination as capital R square? This is usually called multiple coefficient of determination. R square measures what proportion of the total variation in the dependent variable explained by the entire model. In other words, all independent variables, how they are explaining the total variation. So, R square is in fact is measured as the error sum of square. The error that has been created is due to the total sum of square. How much is the error component out of the total sum of square is basically called R square. And what do you mean by error? Basically error is of how much it explains from the model, okay, and how much was the residual. So, TSS minus the RSS is nothing but called sum of square errors. So, 1 minus RSS divided by TSS is called capital R square. Now, this is RSS residual sum of square or this is regression sum of square is notated as regression sum of square noted as epsilon, okay, estimated divided by the total sum of square. So, we have explained. Now, question arises here after estimating this, what is the range of this formula or this value. We know that we have taken r square, it is not only r could be minus 1 to 1, but when we take square of it, the simple term converted to positive. So, in that case the maximum ranges are from 0 to 1. So, minimizing RSS regression sum of square implies that maximizing the R square. That means, when this component is lesser, this is lesser 1 minus this one. So, that means R square is going to be higher. So, accordingly you can do it. So, R square therefore is between 0 and 1. The closer it is to 1, the better is the fit. The closer it is to 0, the worse is the fit. Okay. So, this is one of the important interpretation. R square is no decreasing function of the number of explanatory variables, okay, or regressors present in the model. When your regressors are rising, it is not decreasing, rather R square is fitting to the model. Okay. It's no decreasing function of the number of explanatory variables. When your explanatory variables are rising, it is not a decreasing function, rather it might be an increasing function. So, there might be positive relationship between rise in the explanatory variables to that of the fit in the model. So, basically like suppose you wanted to estimate estimate any context, let it be on healthcare. You wanted to estimate the impact of food quality on quality of healthcare, on medical expenditure, let it be, okay, food quality food consumption and on medical expenditure. So, it might happen that you have taken very specific variables, okay, very limited variables, 2 or 3 variables, and you wanted to feel that your R square value should be very higher. But one suggestion we usually give to our researchers that while your R square is low, you should actually first attempt, you need to fit your model through including the most important variables. When you increase your variables, it is expected that your model is going to be better fit. So, there are other couple of suggestions also, like R square, if it is very low, then which kind of data you are looking at, whether it is cross sectional or not, whether it is cross sectional panel or not, whether it is time series or not. When as we know that when your data is more or less repetitive in future, okay, or almost the same trend line is being followed, that means your line that is fitted is going to be most closer to the one which you have dealt in the previous round of data. Okay. So, when your data is time series kind, R square value is expected to be much higher. When it is cross sectionals, there are huge variations in the data in the cross sectionals observations, therefore, the R square value might be lesser. And in between panel data comparatively gives better value of R square. But even if the data is having represented with less goodness of fit, that does not mean your model is bad. This is one of the indicators where you may cross check. But we need to take enough caution, enough attempt to increase the value of R square. This is what we are guiding, so that your regression model is going to be robust. Number of regressors increases, R square almost invariably increases and never decreases. This is what we have just guided. So, number of regressors has to be higher, okay? Because if one of the variable is explaining around 20% of the total model, if you are including other important variables, those may actually cover up the gaps. Stated differently, that an additional x variable will not decrease R square. Okay. If you are adding another variable, R square is not going to be decreased. So, R square we have discussed. Now, another important dimension in a model is called adjusted R square. Adjusted R square has to be also discussed. That is basically taken with a bar, R square bar, okay, and this is in fact adjusted with the number of parameters in the model, number of regressors in the model. We simply said R square without adjusting its parameter or degrees of freedom. When you adjust or you conditioning upon your constraints in the model, okay, constraints in the model, if they are conditioned, and then your R square value is actually better resulted. So, R square value adjusted could be negative as well, okay, we are just coming to it. So, like the disadvantage attached to the R square measure is that it is an increasing function of the number of regressors. It means more the number of regressors, higher the value of R square, this is what we have said. But in case of adjusted one, when your degrees of freedom are very less, of course you may not able to may not able to fit the data to the model. Okay. In that case, adjusted R square give the right picture. Okay. You are not just simply go in including more independent variables. Independent variables might be redundant as well, those may not explain the model rightly. Okay. If you are simply including it, your adjusted R square is going to be very less. So, it might be negative also, it is not necessarily be increasing every time. To avoid this problem, another measure is used to assess these number of regressor issues regarding modulus of fit. It is called adjusted R square. Adjusted R square explicitly takes into account the number of regressors included in the model. Okay. This is what is in fact the answer which we have discussed. This is denoted with R by R square and computed is 1 minus R square, and it's degrees of freedom. Okay. So, basically what is this? We are trying to get the value of R square. This is nothing but R square, it adjusted with n minus 1 in the numerator divided by number of parameters, that is k. So, the word adjusted here means adjusted for the degrees of freedom, which depends on the number of regressors that is called k in the model. If k is greater than 1, then adjusted R square and its bar, that is adjusted R square, R bar square is less than that of R square. This is going to be an important question in almost all the analytical context. Okay. So, if k is greater than 1, then adjusted R square is going to be lesser, and it is usually the case. Of course, in multiple regression your k is greater than 1. Okay. Then the number of regression in the model increases. So, adjusted R square becomes increasingly smaller than that of just R square. The R square is always positive, but the adjusted R square can sometimes be negative. Okay. So, this is to be highlighted, and it is very important in your preparation. So, adjusted R square often used to compare two models that have the same dependent variable. Adjusted R square is useful comparison. So, adjusted R square is adjusted for the number of independent variables. So, it will increase only if the new variable increases the explanatory power of the model more than would be expected by the chance. So, next one is called pseudo R square. Pseudo R square is though less often used, it is specifically discussed in some context, some of the particular model. it's not called R square, it's called shadowed by certain degrees of freedom, so shadowed by certain goodness of fit. The parameters in a logit model are mostly estimated by maximum likelihood estimation, not by the regression coefficient. It is not a coefficient, it is through the maximum likelihood estimation. This iterative procedure maximizing the likelihood function. Okay. Unlike OLS, R square, R square OLS based R square, the log likelihood LL based estimation gives the pseudo R square value that do not represent the proportion of explained variance, but rather the improvement in the model likelihood over a null model. So, basically when we are actually discussing certain likelihood of being included in a variable in a model. So, actually each fractional points are not discussed in that particular model, they are not discussing the marginal effect as such. So, each of the represented variance are not actually captured in those kind of limited dependent models. So, the log likelihood functions gives certain values about R square, but those are called pseudo. The null model contains no parameters, but the intercept. Pseudo R square are used for evaluating single models, comparing different models to identify the model with the best fit. Pseudo R square based comparisons of different models using the same sample are straightforward. Comparisons of different models resting on several samples can be reliably processed only as long as the pseudo R square used is free of explicit sample effects. More than 80% of publications that report a pseudo R square do not specify which measure they used, as per the author we have mentioned. There are various pseudo R square reported in different articles. Some of are by default available in Stata like McFadden, this one is by default available. Okay. There are other frequently used methods as well. We are not going to the depth of it. Those who have interest to do further research, they can read between the lines and read correctly. There are different ranges also defined for their R square values, pseudo R square values. So, McFadden and others like R square of these MFP, MFH as we have mentioned in this table and MFHJ, which specifically try to tax the inclusion of a high number of independent variables in logit model. Also like we discuss about adjusted R square and R square, it includes degrees of freedom. The number of variables included in the model are also adjusted with the model of R square, adjusted R square model or value. Similarly, here also there are different suggestions given. All pseudo R square are lower in binary than in multinomial logit models. Okay. So, if it is binary, that means we are not actually explaining the other variation due to more variables. So, when there are more multinomial logit models, that means explanations are actually given by third category in the dependent variable. Okay. In that case, accordingly the value of R square are different. Although for McFadden pseudo R square and its adjustment, this effect is not significant. Using the same benchmark values for all pseudo R square, since different pseudo R square vary significantly from each other in value. Same benchmark value of pseudo R square also used. Researchers should report which pseudo R square has been used in their analysis, that is more important. For separate evaluations of logit model, we recommend the pseudo R square by which overall it shows the weakest dependence on the investigated sample design parameters and is therefore specifically fit for benchmarking. So, McFadden pseudo R square we have already said that this is mostly used by the Stata software. McFadden R square and it is the default pseudo R square value reported by Stata package. this measure is defined as McFadden R square is equal to 1 minus log of LC divided by log null. Okay, LC denotes the maximized likelihood value from the current fitted model divided by the null, that is basically denoting the corresponding values but for the null model. The null model with only an intercept and no covariates are discussed. So, some of the important points we are finally going to comprehend and explain. In time series data, it is really easy to get a high R square value because of the train components in the data. But in cross section data and panel data, we usually get low values of R square, and this is quite common. Low R square is perfectly acceptable. It is not going to be making much problematic. Okay, not going to be problematic. R square just measures the proportion of variation explained by included explanatory variables out of the total variation in dependent variables. Other model fitness and adequacy measures should be focused, such as individual significance of coefficients and overall fitness of the model using T and F statistics respectively as well. Additionally, look at multicovariancy and heteroscedasticity to find out the right approach. So, we can explain you with the help of Excel sheet just for your reference. I am not going to explain in detail since we have already covered the time. I am just going to show it through our Excel sheet example. If you just wanted to calculate in your survey data as well, you can follow this approach. Okay. Those formula should be entered very correctly, and you can able to get the result rightly. And here in your screen the worksheet which we wanted to show it to you, like y values we have and x value we have. Okay. Now what we will do, we will find out the estimated value y bar. We have taken some of these values are derived. So, like here you can just have a check. You can just click and you will find out the y values and x values accordingly. Okay. So, and then we have taken their x square, then y square. Okay. Likewise, it is required in our estimation. Then it is the between these coefficient x and y. Okay. Then the capital the y and capital X, that those are the observed variables. Okay. Estimated variables we will also require. So, capital y square and capital X square is also calculated, y estimated, and the error we can also estimate. And once the error is estimated, basically y minus y hat, isn't it? So, once that is done, all the if you click on each of the component, you will find the commands, and accordingly its square will be taken, that is basically called E square, EI square. Okay. So, so y estimated value minus in the n column y estimated value minus the mean value of y, this is what we have already discussed in the diagram, and we will take the square term at the last square here. So, so finally, the slope coefficient is defined as xy divided by x square. This is what at the bottom we discuss everything. Intercept coefficient, that is mean of that y minus beta value times its mean value of x, and variance of this coefficient can be also derived. Error variance, then then variance divided by its 1 plus n 1 upon n plus mean value of x squared, and its error variance adjusted with the degrees of freedom. Okay. Then its square root of each of those variance is derived. After doing these minimum estimations, we require for our calculation. So, what is that? The mean multiple r square we can calculate like this. Okay. And then the r square value, that is basically 1 minus RSS by TSS, this is calculated here, total sum of square. Then adjusted R square is also calculated with the help of its degrees of freedom. We have already all defined its degrees of freedom correctly, and number of observation in this case is 13. Okay. So, and accordingly you can able to calculate. Rest of the details, once you click on this particular table, all its commands we have said, and that will be useful for your calculation correctly. So, I am not going to much detail of it since we have already crossed the time for this particular lecture. I am just going to not going to save, so that next time it will be easier for you to clarify. So, this is what we have done it. So, finally, we have shown one Excel sheet to you, and that Excel sheet is going to be very useful those who wanted to work for a small scale of data, but in large scale of data you have to go give these commands, and there are readily available commands as well to calculate the R square values. So, with this I think I need not explain much. We will look forward for your observation in the next class. Thank you.